So the work that I'm going to describe here concerns code generation and improving the process of writing code generators. Code generators for usually third-generation languages is a key element of model-driven engineering approaches, which enable considerable improvement in the effectiveness of development and the speed of development by automating the code generation process. But the actual construction of code generators is a complex matter. It requires considerable expertise in both the starting language, which might be a subset of UML, and in the target language, which might be a language like Java or C or Python. So these code generators require significant manual effort to write and indeed to maintain, and we can find examples that have taken several person years to construct. So it's important for the usability of model-driven engineering to improve the construction of code generators. Now, what we propose to do is to use some machine learning approach to do that, but in particular a symbolic machine learning approach. So existing code generation techniques have mainly been manual coding, and these can be divided up as model to model, where someone writes a model transformation in a language like QVTR to map from models representing the source language specification to models that represent the target language program. This, of course, requires expertise in the model transformation language as well as in the source and target meta-models. Model to text is perhaps the mainstream approach, where template languages based on the structure of the target language are used to generate target text, and these are filled in from information from the source model. So here again, knowledge of the source meta-model is needed. And then we have target to text languages, where the source text is mapped to target text, and this is usually based on a grammar of the source language rather than on a meta-model. Then there are machine learning approaches, and the machine learning approaches that are relevant have principally been learning translations from one 3GL to another 3GL, for example, Java to Python. And the two main approaches, one based on a bilingual corpus, rather similar to mapping English to French. They have a big collection of data representing corresponding texts in the different languages, and learn by some encoder-decoder approach the correspondence. More recently, there have been approaches based on unilingual corpuses, where we have separate, not coordinated databases of individual language examples, and then the translation is based on alignments recognizing corresponding keywords and elements of the different texts. Now, these certainly reduce the manual effort, but they require very large data sets in multiple gigabyte size data sets, and they also produce an implicit translation. There are not explicit rules which describe what the translation is. So what we want to do is, instead of implicit machine learning, we want to have an explicit machine learning approach which generates explicit rules. And the rules we want are to be written in this text-to-text code generation language called CSTL, where we have translation rules which have a left-hand side that's in the source language text, and on the right-hand side that's in the target language text. And these are concrete text of the individual languages. And we may have conditions to say when a rule applies. Here we don't have source or target meta-models. Instead, the left-hand side is essentially a pattern matching nodes in a parse tree of the source language elements, so it's based very much on the grammar of the source language. Here's some example rules for translating OCL types to Java types, integer mapping to big integer, OCL any to object, and so on. And we can have parameters or variables in these rules, and these variables represent a valid bit of text that might be there. So, for example, a parameterized type set of something maps to Java's hash set with the same parameter. But on the right-hand side, this variable _1 represents the translation of whatever was in the source. So that allows you to use these rules recursively. So the goal of our procedure is to automatically derive such a translator, such a code generator, from a set of examples of corresponding text in the source and target language. And we expect, well, we want the generator to be correct with respect to that data set, and also to be correct with respect to a validation data set in the same way that we normally have with machine learning approaches. We need to validate the translation using a disjoint set of examples. We can call this process code generation by example, or CGBE. Thus, from a data set of examples of types like this, we'd like to be able to derive the corresponding CSTL rules which map obviously individual items correctly, but also can abstract from the examples, say the two examples of a set here, to a general rule for any parameter, and likewise for sequences from these two rules abstract a general rule. From these two examples, abstract a general rule. So that's the key element there. Now this involves three stages. First of all, we start off with a text data set. That text data set needs to be converted into abstract syntax trees, because we're going to learn rules based on the parse tree structure of the source and target text. So we end up, from the data set of text, we end up with a data set that's in terms of abstract syntax trees. Given those trees, we then, using a search-based procedure, try to recognize correspondences from the source to target tree structures. And finally, we convert those tree-to-tree mappings into CSTL rules. So the procedure works like this. We start with a text data set, convert that to parse trees, we get a syntax tree data set. There's some information about the language categories, and mainly this is the source language categories, which usually correspond to the grammar, non-terminal and terminal grammar elements of the source language. The target language can be very general, just in terms of expression, statements, types, and so on. It doesn't need to be distinguished. We specify an outline mapping, for example, source expressions mapped to target expressions. And we use model transformation by example approach to recognize those tree-to-tree mappings. It's a systematic search-based approach which is looking for corresponding structure from source to target data, in this case, the syntax trees. We end up with then a schematic tree-to-tree mapping, and we convert that schematic mapping to CSTL. Now, code generators are based on the structure of the source and target language. Normally, the structure of a language is quite systematic, with types, expressions, statements, operations, attributes, classes, and so on. And that structure is used in defining the code generators and learning the code generators. Now, there's various representations that could be used for programs, the simplest being text or sequences of tokens, but we are using syntax trees, and the reason for that is that syntax trees provide more detailed structure about the actual structure of the data, the semantics of the data there. Now, syntax trees mapping can be in many different forms. One typical form is where we elaborate a single tree node into a nested tree node. That's like adding a branch into the tree. We can add new elements where we elaborate a tree by adding in new things. Here, for example, sequence of I can be elaborated to be sequence of I minus 1 if we're shifting from one language with different indexing. For example, OCL has indexing starting from 1, but Java has indexing of arrays starting from 0, so we need to subtract 1. As a tree structure, that means our source expressions are going to look like this. They have a subtree. That subtree is going to correspond to the target subtree here. So the rest of the structure is essentially the same. 4 nodes here. It's the third node that gets elaborated to be an elaborated third node. So it's recognizing that correspondence from a number of similar examples where the actual identifiers here change, but otherwise the structure is the same. We can also have functional mappings where some token in the source is mapped to a function of that token. For example, the operator symbols like not in OCL becomes exclamation mark in Java. We can reorder the elements of a tree and we can generally change the tags, renaming tags, and do lots of different transformations. In general, if we have a target tree like this with n subterms, we can look for correspondences based on the individual subtrees. So we need to find for each ti here some source term or combination of source terms which produces that t. For example, in going from a unary expression like this, where we have a something and then an operator and then a couple of brackets, in Java that might map to an application of the math library. So we have math dot a method call, and the abs here corresponds to the abs there, and the expression in the parameters corresponds to the first subtree of the source. So here we're reordering the arguments, reordering the subtrees. This first tree becomes now the third subtree of, in fact, the second subtree of the top, third subtree of the top. So quite a complicated reordering of structure, but there's still that correspondence can be recognised. And we can also have variable numbers of terms in each tree. Here's another example of identifying correspondences between lambda expressions in OCL. We might have text like this, lambda x type string in x plus x. In Java, that would be an expression like this, x arrow x plus x. And we could have several examples of that form. Corresponding trees look like that. And we can recognize, for example, that here this part corresponds to this part, and this type is actually discarded in the target, and the argument here corresponds to the argument there. So we end up with a schematic rule which looks like this. The OCL basic expression, that's the parameter, becomes the lambda parameter in Java, and the type is discarded. That's item 2. Variable 3 becomes the actual expression of the lambda expression. And as a CSTL rule, that schematic rule looks like this. essentially based on the literal text that's derived from this tree. Lambda 1 of type 2 in 3, and that gets mapped to lambda 1 underscore 1 to underscore 3. Okay, so we evaluated this on translation from OCL and UML to Java, and also from OCL UML to C. And here you can see the number of examples are actually quite small, with a total number of examples of only about 200, under 200 examples there. The code generator size is also quite small, it's produced from that. And the training time is relatively practical, it's a matter of seconds. The F measured indicates the accuracy on the validation data sets. Likewise for C, somewhat smaller examples here, but again quite practical in terms of construction. If we compare these to manually coded translators, well, we wrote manually some CSTL translators from UML to Java 8 and from UML to Swift for the generation of mobile applications. And these took quite a substantial amount of time, but using the CGBE approach, the amount of time was substantially reduced for code generators of similar complexity. So, in conclusion, we've created a novel symbolic machine learning approach, which is able to learn useful code generation rules based on identifying syntax tree to syntax tree correspondences. And it produces an explicit set of rules, which is one advantage over non-symbolic machine learning approaches, which only created implicit translations. And this approach significantly reduces the manual effort that's needed, because the person doesn't need to manually create the rules, but they only need to create the examples.